Hello everybody and welcome to lesson 2 transportation problem formulation. The learning objective of this lesson is formulation of transportation problem or transportation model from a real business problem so as to get the optimum solution, or the objective of getting transportation model from a real business problem is to ultimately find the solution or the optimum solution that minimizes the transportation cost. One of the most important applications of quantitative analysis is to solve business problems which has been in the physical description of products, commonly referred to as transportation problem. As we know, quantitative analysis have different applications, and one of the application is in the area of transportation problem. Basically, the purpose is to minimize the cost of shipping goods or to minimize the cost related to transportation from one location to another locations. When we move our resources or when we distribute our products from one location to another location, there are two things that should be fulfilled. The first one is the needs of each arrival area should be fulfilled, or the requirements, or we can say the demands of the warehouse it can be, or the customers have to be fulfilled. And the second is every shipping location operates with its capacity, or every supplying location have to be operated within or less than or equal to its capacity. So these are the two constraints that have to be kept in mind. And our objective is ultimately to minimize the cost of transportation. So to obtain a feasible solution, the total supply must be greater than or equal to the total demand. To obtain a feasible solution for the transportation problem, total supply have to be greater or equal to the total demand. Or we can say a balanced transportation problem has always a feasible solution if the sum of the supply and the sum of the demand are equal. So we call it a balanced transportation problem, and a balanced transportation problem has always a feasible solution. Let's move to an example which is a balanced transportation problem. That means the sum of the supply and the sum of the demand are equal. And a company has three production facilities, S1, S2, and S3, with a production capacity 7, 9, and 18 units per week, respectively. These units are shipped to 4 warehouses. We have 4 warehouses from the demand side, that is D1, D2, D3, and D4, with requirements or with a demand 5, 8, 7, and 14 units per week, respectively. The transportation costs per unit between factories to warehouse are given in the following table. As you see here, this table describes the cost, the per unit cost to transport from each facilities or each production facility to each of the warehouses. So to transport an item from S1 to D1, it takes 19 birr, or we can say $19. To transport from S1 to D2, that means a single item, so $30. To transport a single item from S1 to D3, it takes $50. To transport a single item from S1 to D4, it takes $10. And the capacity of S1 is, the maximum capacity of S1 is 7, and the same is true for the remaining. If we take, for example, 70 is the per unit cost to transport a single item from S2 to D1, and the capacity of S2 is 9, and the capacity of S3 is 18. And this row shows the demand or the requirements of each warehouse. For example, D1 requires 5, D2 requires 8, D3 requires 7, and D4 requires 14. When we add 5 plus 8 becomes 15 plus 7, 22, 22 plus 40 equals 34. Let's add again. 5 plus 8, 13, 13 plus 7, 20, 20 plus 14, 34, yeah. Let's add the capacity. 7 plus 9, 16, 16 plus 18, 34. So, as you see, the supply, the sum of the supply and the sum of the demand, these are the sum of the supplies, or the capacity we can say. The summation of the capacity equals the summation of the demand or the summation of the requirement, that is 34. So we can say this problem as balanced. We can consider this problem as balanced transportation problem because the sum of the supply and the sum of the demand are equal. So it has a feasible solution. It has an initial feasible solution because this is a balanced transportation problem. Let's now start the graphical representation of this transportation problem. The graphical representation looks like this. So we have to put S1, S2, S3 along with their capacities here, and let's put the demand side, that is the warehouse, the 4 warehouses along with their requirements here, and then these are the routes. The routes, we have 4 routes from each supply side or from each production facilities, because from each production facility we take to all of the 4 warehouses. So we have 4 routes, 4 routes, 4 routes. So we can write the costs to transport an item from S1 to D1 here. The cost is here 19, and the cost for S1 to D2 is 30, and here is 50, and here it is 10, and the cost from S2 to D1, S2 to D1 is 70, so we have to write here 70, then here 30, then here 40, then 60 here. And from S3 to D1, S3 to D1 is 40, then here we write 40, then here we write 8, then 70, then 20. So this is just a graphical representation of the transportation problem. To formulate this transportation problem, let's nominate that Xij is the number of units of the product to be transported from I, that is I represent 1 to 3, the 3 production facilities, to the warehouses. We have 4 warehouses, so J equals 1, 2, 3 to 4. So the transportation problem is stated as, since our objective is to minimize the total cost of transportation, and the total cost of transportation can be calculated by the per unit cost times the number of items to be transported. So from this table we can understand that X11 is the number of items transported from 1 or S1 to D1. So the first subscript represent the production facilities or the suppliers, and the second subscript represents the J. It means the J represents the 4 warehouses. So the first is represented by I, that is the production facility or the suppliers, and the second is J, which represents the 4 warehouses. So X12 is the number of items to be transported from S1 to D2, and the same is true for the remaining. So to find out the transportation, we have to multiply by the per unit cost times the number of items. When we multiply the number of items times the per unit cost, so we get the transportation cost from S1 to D1. But our objective is to find out the transportation cost, the overall transportation cost to transport items from all our production facilities to all our warehouses. So minimization of Z equals 19 times X11. This is the transportation cost, transport from S1 to D1, and here it is from S1 to D2 and from S1 to D3 and from S1 to D4. And the next is, this one is the transportation cost from S2 to D1, S2 to D2, S2 to D3, S2 to D4. And this is the transportation cost from S3 to D1, S3 to D1, S2 to D1, S3 to D2, S3 to D3, S3 to D4. So this is the overall transportation cost. So our objective is to find them, to minimize this transportation cost. And subjected to the constraint, we have, as we previously said, that we have two types of constraints. That is the capacity constraint, because each origin has a limited supply. For example, S1 has only a capacity of 7, S2 9, and S3 is 18. So we have 3 supply constraints, and we have also requirement constraint, because each destination has a demand requirement of, for example, D1 requires 5, D2 requires 8, D3 requires 7, and D4 requires 17. So we have 4 constraints of requirements, and the other is non-negativity. Actually, we will see it on the next slide, the detail of the 3 constraints. There's 3 capacity constraints and 4 requirement constraints. And before that, let's assume that M represents the suppliers and N represents the warehouses. So M times N, that is 12 decision variables. We have 12 decision variables. We have 12 decision variables, X11, X12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have M times N, 12 decision variables. And we have 7 constraints, M plus N. M represents suppliers and N represents warehouses. M plus N equals 7. So we have 7 constraints with 3 capacity constraints and 4 requirement constraints. And let's see the detail. So to start from supply constraints, we have 3 distribution facilities. So all the items transported from S1 to all the destinations, all the 4 warehouses, cannot be greater than or should be less than or equal to 7, should be less than or equal to the capacity of the facility 1. And the same is true for the second supply capacity, that is all the items transported from facility 2 to all the warehouses should be less than or equal to the capacity of the facility, that is 9. And all the items to be transported from facility 3 to all the warehouses should be less than or equal to 18. That is the capacity, the maximum capacity of facility 3. So these are the supply constraints. We have 3 supply constraints. And second, we need to ensure that each warehouse will receive sufficient stock to meet its demand. For example, warehouse 1 must receive at least 5 units because it requires 5 units. So we obtain the demand constraints by equality X11 plus X21 plus X31. That means the items transported from facility 1, facility 2, facility 3 to warehouse 1 should satisfy the needs of, or should satisfy the demands of warehouse 1, that is 5. And the same is true for the remaining. For the warehouse 2, all the items coming from the 3 production facilities have to be equal to its capacity. And the next is warehouse 3, sorry. All the items coming from the 3 production facility have to be equal to the demand requirements of warehouse 3, and the same is true for the warehouse 4. And the last one is the non-negativity, that is Xij must be non-negative, that is greater than or equal to 0, where I represents 1, 2, 3, that is the warehouse, the production facilities, and J represents the warehouse, the 4 warehouses. So this is how to formulate transportation problem from a real business problem. In general, our objective is to minimize the cost of transportation, and keep in mind that we have to fulfill the requirements, and we have to keep the capacity requirements and the requirement constraints. Let's move to the unbalanced transportation problem. In the case of unbalanced transportation problem, the total supply, that is the summation of all supply, is not equal to the summation of the total demand, summation of all the demands. So in this case, we can say unbalanced transportation problem. Let's consider case 1. If the total supply exceeds the total demand, if the supply exceeds the total demand, no modification in the linear program formulation is necessary. So the previous formulation works for this case. What we formulated previously works for this. If the supply exceeds the total demand, and excess supply will appear as a slack in the linear programming solution, and slack for any particular origin can be interpreted as unused supply or amount not shipped from the origin, because already since the supply is greater than the demand, so the demand is fulfilled with only some portions of the supply. So some portions of the products cannot be, or some portions of the items did not be transported to the demand side or the warehouse, because already the warehouse is filled, or the warehouse requirement is already attained. Let's move to the case 2. If the total supply is less than the total demand. If the total supply is less than the total demand, it's obvious that some of the requirements or some of the demand may not be filled. So the linear programming model of transportation problem will not have a feasible solution in this case. It doesn't have a feasible solution since some of the demands cannot be fulfilled with lack of the supplies. So in this case, we have to add a dummy origin, a dummy supplier having equal to the difference between the total supply and the total demand. So the dummy has an amount, with the difference of the supply, total supply, and the total demand. Or we can say that we can subtract total demand from total supply to nominate a value for the dummy variable, or the dummy suppliers. With the additions of the dummy origin, the linear programming model will have a feasible solution. And a zero cost per unit is assigned to each arc or to each route leaving the dummy origin, because the logic is that no shipments actually will be made from the dummy origin, right? We just assign a dummy suppliers having the difference between the total demand and the total supply, and the transportation cost from this dummy variable to all the warehouses is assumed to be 0, because in reality there is no shipments actually will be made from the dummy origin. The destinations showing shipments being received from the dummy origin will be the destination experiencing shortfall or unsatisfied demand. The destination that shows a transportation of items from the dummy variables is clearly unsatisfied, because there is no, in reality, there is no items in the dummy suppliers. Proceeding to the unbalanced transportation problem formulation example, electric supplier has a company which supplies electric, has 3 electric power plants that supply the needs of 4 cities. Each power plant can supply the following numbers of kilowatt hours of electricity along with the associated cost of sending 1 million kilowatt hour of electricity from plant to city. Formulate a linear programming to minimize the cost of meeting each city's power demand. So we have here, the table shows we have three power plant and four cities to be supplied from these power plants. And these are the costs. For example, to move per unit of electricity to from plant 1 to city 1 requires $8. So 1 million kilowatt hour meter of electricity requires 1 million kilowatt hour requires $8 to transport from plant 1 to city 1. And the same is true for the remaining. So let's add first whether this problem is balanced or unbalanced. When we add this, let's add 45 plus 20, 65 plus 30, 95 plus 30, 125. This is the demand. The demand is 125. Let's add the supply. 25 plus 50, 75. 75 plus 40, 175 plus 40, 115. So it is 115. So since the supply and the demand are not equal, so it is unbalanced transportation with the demand greater than or the supply is less than. The supply is less than the demand. So here, to get the feasible solution, we have to add dummy plant having a power, the difference between the supply and the demand. The demand is 125 and the supply is 115, so the difference is 125 minus 115, so 10. And the transportation cost from the dummy variable, the transportation cost of 1 million kilowatt hour from dummy to city 1 is $0. And the same is true for the remaining cities, because actually in reality there is no electricity in the dummy power plant. We add a dummy variable to get just a feasible solution. So we add like this in the table, and we add, this is a graphical representation of the dummy variable, which has a capacity of 10. So it's supplied to all of the cities. So when we formulate, first of all, we have to represent I represents the power plant. That is, we have 3 power plant, 1, 2, 3, and J represents the cities. So Xij represents the number of million kilowatt hour produced at plant I and sent to city J. So our objective function is to minimize the transportation cost of electricity from the plant to the cities. So 8 means the per unit cost of transportation multiplied by the amount of electricity transported. So this is the transportation cost required from plant 1 to city 1, from plant 1 to city 2, plant 1 to city 3, plant 1 to city 4. So this is the cost of shipping power from plant 1 to all the cities. And the same is true for the remaining. The second one is cost of shipping power from plant 2 to all the cities. And this is the last one is cost of shipping power from the dummy power plant. So this is the objective function, that is minimization of z equals 8x11 6 plus 6x12 plus 10x13 plus 9x14 plus 9x21 plus 12x22 plus 13x23 plus 7x24 plus 14x31 plus 9x32 plus 16x33 plus 5x34 and plus 0x d1 0xd2 plus 0xd3 plus 0xd4. As we said before, the first subscript represents the plant and second subscript represents the cities, sub-cities. And after defining the objective function, the next task is to establish the constraints or to formulate the constraints. Once we establish our objective function, let's move to the constraints. We have two types of constraints, that is the supply constraints, or we can say the plant capacity constraints and the demand constraints. The supply constraint means each power plant can operate with their capacity. They cannot operate beyond, or they cannot operate more than their capacity. So all the electricity provided to the 4 cities from plant 1 cannot exceed the plant 1 capacity. So we can state that x11 x plus x12 plus x13 plus x14, that is the electricity obtained or the electricity provided to all the 4 cities from plant 1 cannot exceed the capacity of plant 1. That is, it should be less than or equal to 35. And the second constraint, since we have 3 constraints, actually we added the 4th constraint, that is the dummy power plant. But in reality, we have originally we have 3 constraints because we have 3 plants. And the second constraint is mentioned like this because of the capacity of the second plant is 50, so it should be less than or equal to 50. And the third is like this. And the last one is the dummy supply or the dummy power plant. So the dummy power plant capacity is 10. So xd1, xd2, xd3, xd4, that is the power provided from the dummy plant to the 4 cities cannot exceed 10 because the dummy power plant is assumed to have a capacity of 10. That is the difference between the total supply and the total demand. So this is what we call the supply constraints. Let's move to the demand constraints. We need constraints that ensure that each city will receive sufficient power to meet its demand, that is the demand requirements. Thus x11, that means the electricity transported from plant 1 to city 1, electricity transport from plant to city 1, from plant 3 to city 1, from dummy plant to city 1 should be equal to 45. That means city 1 demand constraint. And the same is true for the remaining cities. That is, this constraint is expressed with equality or related with equality. And the last one is the negativity, that is xij. Xij, that means the amount of electricity transported from any one plant to the city should be greater than or equal to 0. That is, I represents the 3 plants, 1, 2, 3, and J represents the 4 cities, that is 1, 2, 3, 4. This is all about how to formulate transportation problem from a real business problem. We have already finished today's discussion, so try to do this assessment quiz, and if you encounter a problem, you can write on the comment box. And next time we will meet with finding the initial feasible solution. That means we will find, once we formulate the transportation problem or the transportation model today, so next time we will try to find the initial feasible solution for the transportation problem using 3 methods, that is northwest corner method, minimum cost method, Vogel's approximation method. So till then, have a good time. Bye.